So today we are going to discuss about B+tree index operations. In the last class, we have gone through the properties of B+tree. We mentioned that B+tree is the most widely used index. Right? And it has several advantages over the indexed sequential files. And that is why in database management systems, B+tree structures are being used to store the indices. Right? So we have seen how the node looks like for B+tree. So in B+tree node, we are having n pointers, right? And n minus 1 search keys. So if we are creating a B+tree with having a node with n pointers, then in every node we are having n pointers, and in every node it is possible for us to store n minus 1 search keys, right? So a typical B+tree node looks like this. I'm just drawing it. So we are having n pointers. Right? So this is pointer P1, this is pointer P2, this is P3, so on up to Pn. So in one node, it is possible to accommodate n pointers and obviously n minus 1 keys. So search keys are denoted as K1, K2, K3, so on up to Kn minus 1. Right? Also, we mentioned that if I am having n minus 1 keys stored in a node, then always these keys are stored in order with respect to a particular node. So here we are having K1, which is less than K2, less than K3, so on up to Kn. So the highest value, sorry, Kn minus 1. So the highest value that we are storing in a node is Kn minus 1 and the lowest is K1. So all the keys are ordered. Those are stored in a node. Further, we mentioned that B+tree is actually a balanced tree, right? And it satisfies certain properties. So all paths from root to leaf are of the same length, right? So all paths from root to leaf are of same length. That is one important property of B+tree. Further, each node that is not a root or a leaf has between n by 2 and n children. So if we are talking about the internal node, which is not a root node or a leaf node, then it has ceiling of n by 2 and n children, right, for internal node. Right? A leaf node is having n minus 1 by 2 ceiling of that and n minus 1 values. So if we consider a leaf node, then the values those are stored are n minus 1 by 2 to n minus 1. So those many values can be stored in a leaf node. There are certain special cases. If the root is not a leaf, it has at least 2 children. This means that if in a B plus tree we are having more than one nodes, then always the root node is having at least 2 children, at least, right? And if the root is leaf, that means there are no other nodes in the tree, only one node is there, then it can have between 0 and n minus 1 values. So my tree may be empty, or as I am having a single node in this special case, I may have at the max n minus 1 values. Those are stored in a node. Right? Now, further, as far as the leaf node is considered, and if we are having two nodes, two leaf nodes, Li and Lj, and if I is less than j, then all the key values, those are stored in Li, are less than or equal to all the search key values, those are stored in Lj. Right, that is one important property. For the pointers of the leaf node, for the pointers P1, P2 up to Pn minus 1, right? The pointer either points to a file or to a record with search key value ki. So if I am having a pointer P1, then this pointer, I am talking about the leaf node. So pointer P1 of the leaf node either points to a record with search key value k1, or it points to a bucket where all the records having this search key value are stored, or the pointers to the records having this search key value are stored. Right? So these are the properties of the leaf node. If we talk about non-leaf nodes or internal nodes, then internal nodes are actually forming the multi-level sparse index. Multi-level sparse index. Right? So all the search keys in the subtree to which P1 points are less than K1. So if this is my internal node, then this P1 points to a subtree. So all the keys, those are stored in this subtree pointed by P1 are less than the search key K1. Right? We are having intermediate pointers, say P2, P3 up to Pm minus 1. So all those pointers are actually pointing to the subtrees where the values lie between ki minus 1 and ki. So if I am considering this P2, then the subtree which is pointed by P2 contains all the values. Those are greater than or equal to K1 and less than K2. Right? And the last pointer that I am storing in the internal node, that last pointer is pointing to a subtree where the values stored in the subtree are always greater than or equal to Km minus 1. So, which is this search key Km minus 1? This is the last pointer that I am having. So, prior to that, I am having this Km minus 1. So, Pm is pointing to a subtree where all search key values are greater than or equal to Km minus 1. Right? We are going to look at one example so that you can understand those concepts. So see here the example. We are having a root node, right? So in this particular example, the value n is equal to 4. So every node is having 4 pointers. Right? So in every node, we are storing 4 pointers and maximum 3 search key values. So typically, this is a B+tree index for our instructor file. And this B+tree index is created such that the number of pointers in each node are equal to 4. So see here, we are having a root node. These are the internal nodes and these are the leaves. Right? So root node can hold fewer than n by 2 pointers, but at least 2 if nodes are greater than 1. So here in overall B+tree, we are having more than 1 nodes. Right? So minimum 2 pointers we should have. Right? So we are having here, see, 2 pointers and 1 search key value. Look at these internal nodes. In this internal node, we are having 2 search key values stored, and in this internal node, we are having only 1 search key value. Right? So in internal nodes, at least n by 2 pointers we have and at most n. So for internal nodes, we may utilize maximum n pointers and minimum n by 2, ceiling of n by 2 pointers. So here my n is 4. So minimum 2 pointers I have to use for internal node and maximum 4 pointers I can use for internal node. Right? Look at this leaves. So as I stated earlier, in a leaf node, we may store minimum n-1 divided by 2 and ceiling of that up to n-1 key values. So minimum key values, those we are storing in the node, leaf node, are n-1 divided by 2 ceiling of that, and the maximum search key values, those can be stored at n-1. Right? Now, just see here. This is our instructor relation. And for this instructor relation, we have created the index using B+tree. Right? As I stated, these internal levels are forming the sparse index. Right? But if we look at these leaves, this is forming a dense index, meaning all the search key values are present in either of the leaf nodes. See here how many search key values are there. So here this B+tree is built by making use of search key value, that is name. Right? So this B+tree is built by making use of search key value name. So every individual search key value we are having in the leaf nodes, one of the leaf nodes. Right? So see here, if I want to search for a particular record, then I'll begin from the root node, and according to the rules, I'm going to explain you the rules, how we are going to search for a particular data in a while, right? But just see this example. I need to follow one of the pointers, and this pointer ultimately will take us to one of the leaves, right? And if we follow that pointer, it will take us to the particular record in a file. right? So this is how the B plus tree looks like. In B plus tree, we are having the search key values, right? The leaf nodes or the leaves are having actually all the search key values, right? And the internal nodes are having few of the search key values. So the internal nodes are forming the sparse index, whereas the leaves are having a dense index, right? See here one more example. So once again, this is a B plus tree for instructor relation. But here the number of pointers n equal to 6. So we are having 6 pointers in every node of B plus tree. So leaf nodes must have between 3 and 5 values. Non-leaf nodes other than root must have between 3 and 6 children, and root must have at least 2 children, at least 2. More than 2 are allowed. Right? So all the properties of the B plus tree are followed by this tree as well. So these are 2 examples of B plus tree. In fact, in today's class, we are going to see how we can build such kind of a tree given some data. Right? Is there any doubt so far? Is there any doubt? We are going to build such kinds of trees. Right? We are going to see what are the steps to build such kind of trees given some data or search key values. Right? So let us see now how actually the queries are performed on B plus trees. Right? So suppose we want to find all records with search key value V. What we want? We want to find all records with a search key value V. So, I'm just listing out the steps and then we'll see the example following these steps. So, I would advise you to please note down these steps. Finding all records with some search key value, say V. We have been provided with a B plus tree index and we want to search for the records with value V, right? So obviously we are going to start with the root node, right? So begin with the root node of the B plus tree and set it as the current node. Now examine the node for the smallest I such that search key value ki is greater than or equal to the value that we are looking for, V. I repeat, examine the node for the smallest I such that the search key value ki is greater than or equal to V. Such a value exists, then assume that it is ki. Then we will check if ki is same as the value that we are looking for. If ki is equal to v. If ki is equal to v, then follow the pointer pi plus 1. Right? And following this pointer, see for example, here I am having say K1, P1, K1, P2, K2, so on up to Kn minus 1, Pn. So we are having always n minus 1 search key values and n pointers in a node, right? So we will begin from the root node and we are going to examine the root node for the smallest I such that search key value ki is greater than or equal to the value that we are looking for. If such a value exists, so let us assume that it is ki. Say for example, this is say k1. Then if my k1 is same as the value that I am looking for, right? So if my k1 is same as v, then what I am going to do? I am going to follow the next pointer, right? So if my ki is v, then follow pi plus 1. So here in this particular example, my I is 1, right? So I'll be following P2. So this P2 pointer will take me to some node. So whoever is the child node, now this node will become the current node. In this situation, if Ki is equal to V. Now, otherwise, that means if Ki is not equal to V, then what I'm going to do? Ki is greater than V, right? Ki is greater than V. In this situation, I'll be following the pointer Pi. So if my K1 is greater than the value that I'm looking for, then obviously that value will be present in my subtree, which is pointed by P1. Right? So if Ki is greater than V, then I'll be following the pointer Pi. Right? So in this case, if my K1 is greater than V, I'll be following this pointer P1. So this pointer P1 will take me to some child node. So in this situation, that child node will become the current node. Right? Now, if no such Ki is found, then clearly V is greater than or equal to the last key value that is stored in the node. Right? So in this situation, what I will do is I will follow the last not null pointer, and this pointer will take me to another subtree. So I'll be following pointer PM, and that will take me to the another subtree, and that child node is now set as the current node. So we are having three conditions here. What are those three conditions? I am looking for some value V. Right? So I will be looking for this value. I'll begin from the root node and I'll check the root node for the smallest I such that the search key value Ki is greater than or equal to V. If it is equal to V, then I'll be following pointer Pi plus 1. If Ki is greater than V, then I'll be following pointer Pi. And if there is no such Ki, then clearly the value that I am looking for is greater than or equal to the last search key value that is stored in the node, Km minus 1. So obviously, I need to follow the pointer PM, the last not null pointer. So in any of these cases, I'll be coming to a child node, right? So that child node now becomes the current node. So if the node reached by following the pointer above is not a leaf node, Then repeat the procedure on the node and follow the corresponding pointer. So the same procedure gets repeated if the node that I have reached is not a leaf node. Right? If it is not a leaf node, then once again the same procedure is followed. Eventually, we reach to a leaf node. So whenever we reach a leaf node, if for some I, the key ki is same as the value that we are looking for, then we are going to follow the pointer pi, and this pointer will take us to the desired record having the value v that we were looking for. Otherwise, there is no record with the search key value v that we are going to declare. So this is the procedure how we can find out the records with a particular search key, say v. Now practically we'll see how such kinds of queries are being used with b+tree. So see here, we are having this b+tree with n equal to 4, and this b+tree is meant for the instructor relation, right? And the search key value or the search key that is used to build this b+tree is name of the instructor. So this name. Right? Now, let us assume that we would like to find the record for search key value gold. Right? Now, we are going to follow our algorithm. So we will begin, so this is the b+tree that we have. So we will begin from the root node. Right? Now, what we are going to do first, we are going to examine this root node for the smallest I, such that ki is greater than or equal to gold. Right? Smallest I such that ki is greater than gold. Now, in this particular root node, we are having only one search key value. So this is my k1. Right? I am having only one search key value here, and that is Mozart. Right? So I'll be finding out whether this search key value Mozart is greater than or equal to gold. So it is not equal to gold, but it is greater than gold. Right? So Mozart is greater than gold. Right? So if this is greater than gold, then we are going to follow pointer P1 according to our algorithm. Right? So this is my pointer P1. So I'll be following this pointer P1, and this pointer P1 will take me to the next node, the child. Right? Now this will become my current node. And as this is not the leaf node, the same process I need to follow. So I am looking for gold. So once again, what I will do, I will find for this node now. This is my current node. So for this node now, I will be finding out smallest I, such that ki is greater than or equal to gold. Right? Now, here, this is my K2 and this is my K1. And my K2 is same as the value that I am looking for. Is that correct? So, I am finding out this K2 here, which is same as the value that I am looking for. So if it is equal, then we are following the next pointer. So I'll be following this P3, the next pointer. So this next pointer will take me to this particular node. Right? Now, this node happens to be the leaf node. So if I have reached to the leaf node, then there are two possibilities now. I may find that key value in this leaf node. Right? So see here, if I sequentially now search for the value that I wanted, then I find that in this leaf node I am having that value gold. And this is the key value K1. Right? Now, in this situation, what I will do? I will follow this pointer P1 from the leaf node. And this pointer P1 will take me to the record where I am having this value that was desired, gold. So I wanted to search for the record of instructor gold. And I have used the B+tree index that was built as per the search key value name. So after following few of the nodes, it is possible for me to reach to a particular record, and that is gold in this case. Okay, right. So let's proceed now with one example demonstrating how actually the B+trees are efficient while searching for the data from the database, right? In processing a query, a path is traversed in the tree from the root to one of the leaf nodes. So always, whenever we want to search for any particular record, we begin from the root node. And according to our algorithm, we follow some path and ultimately we reach to a leaf node. So in processing a query, a path is traversed in the tree from root to one of the leaf nodes. Right? Now, if there are k search key values in the file, if there are k search key values in the file, the path is no longer than log of k to the base ceiling of n by 2, where this n is number of pointers in our B+tree node. I'll repeat. If there are k search key values in the file, then the path is no longer than log of k to the base n by 2 and ceiling of that. Right? Let me illustrate this with one example. Suppose a node in B+tree is of size 4 kilobytes. Typically I am saying the size of disk block is used as the size of the node. So a node is generally the same size as the block size. And typically if a disk block, we assume if it is 4 kilobytes, then my B+tree node is of also size 4 kilobytes. And number of pointers n is typically around 100. So 40 bytes are used per index entry. Right? So this is a general statistics that we have. Usually one node is one disk block. Right? So obviously the size is 4 kilobytes. And typically the number of pointers of B plus tree n equal to 100. So 40 bytes are utilized to store one index entry. Okay, now with 1 million search key values, 1 million means 10 lakh. If we are having 1 million means 10 lakh search key values in our database, in our relation. See, we are talking about huge database files having lots of data. So in real world scenario, it may happen that we are having millions of search key values, right? So we are assuming right now that we are having 1 million search key values. That means 10 lakh search key values. And as we assume that number of pointers of B plus tree node are 100. So if I am having 1 million, that means 10 lakh search key values. And if n is 100, then obviously how many nodes I need to access to search for a particular search key? On an average, I need to traverse log of k to the base n by 2. So here log of k is 10 lakh to the base n by 2. That means 50. So log of 10 lakh to the base 50. So this comes out to be 4. Right? So if I am having a B plus tree wherein I am storing 10 lakh search key values, and if my B plus tree is having 100 pointers per node, then on an average, if I am searching for a particular record using this B plus tree index, then only 4 nodes I need to access. Are you getting me? Yes, please try to understand. Are you getting me? See, if I am having a tree like this, then ultimately I need to reach to the leaf node, and this leaf node will take me to the record. So if I am searching for a particular record, and in this particular real world example, I am having 10 lakh search keys, and this every node is having 100 pointers, and every node is stored in one disk block. Right? Then on an average, if I want to search for a particular record, then how many nodes I need to access? Log of k, that means 10 lakh, to the base n by 2. So this comes out to be 4. So I need to access 4 nodes to search for a record. Right? Having 10 lakh search key values, different search key values. Right? So I'm searching a record from a huge relation. Right? And still I need to access 4 nodes, meaning I need to access 4 disk blocks. Right? So if we compare this with our normal balanced binary tree. So this is with respect to B plus tree. This statistics is with respect to B plus tree. Right? Now, if we compare this B plus tree statistics with a balanced binary tree. So it is possible for us to build the index by making use of balanced binary tree as well. Continue our discussion. So if we compare our B plus tree index with a binary tree index with similar 1 million search key values, right? Then if I'm using a balanced binary tree to carry out the same task with 1 million search key values, then I would require 20 node accesses. So I need to access 20 nodes to come up to the desired record, right? So see the difference. If I am using B plus tree, then I'll require 4 node accesses, whereas if I am using binary tree, then I'll require 20 nodes to be accessed to get to a particular record. So obviously you may observe here that B plus tree are much more efficient than the binary trees. So this difference, 4 nodes and 20 nodes. So this difference is significant, right? Because if we assume that every node access requires disk input output operation. So one disk IO operation, if it costs around 20 milliseconds, then to access 4 nodes, we will require only 80 milliseconds. Whereas if we are accessing 20 nodes, then 400 milliseconds will be required to get to a particular data. And this is the significant difference if we go with B plus tree and if we go with simply a binary tree. Right. So let's move on to the updates on B plus trees. And we'll look for the insertion operation first, and then we will go for deletion operation. Right? So if we would like to insert some record in our relation, then obviously for that particular record, whichever is the search key value, we need to look for that search key value in our B plus tree index. If that search key value is already available in our B plus tree index, then no issues, right? But if that search key value is not available in our B plus tree, then we need to insert that search key value in our B plus tree. So we are going to look at the procedure, how we are going to insert the search key values in our B plus tree index. Right? Now, the first step is find the leaf node in which the search key value would appear. We would like to insert now. We are not having the search key value in our B plus tree and we would like to insert it. So what we are going to do first is we are going to find out the leaf node in which that search key value should be inserted. Right? So we begin from the root node. We go on following the respective links till the leaf node, and we are supposed to find out the leaf node where that search key value should be inserted. Now, if the search key value is already there in the leaf node, then record is added to a file, and if necessary, a pointer is inserted into the bucket. This is the routine procedure. If the search key value is already there, then we are not going to do anything, right? But the record is added into the file, and if required, the pointer that points to that particular record gets added into the bucket, respective bucket. If the search key value is not there, then we are going to add the record into the file and we are going to create a bucket if required. And then what needs to be done is that search key value, which is new now, needs to be inserted into the leaf node. Right? Now we have identified the leaf node. So we are supposed to insert that new search key value in the leaf node. Right? So if there is space available in the leaf node, then directly we are going to insert that key value along with the pointer in the respective leaf node at appropriate position. But if there is no room in the leaf node, then we need to split the node. Splitting the node means as the leaf node is full, we need to add one more leaf node. And this process is known as splitting the node. Right? So, how to split the leaf node? That procedure we are going to discuss next. Right? Say for example, this is my leaf node. Right? And a new search key value that I want to add in this leaf node is say Adams. Right? Now, this leaf node is full. So there is no space to accommodate this search key value Adams. So what it does is, it splits the node. So this node is now being converted into pair of nodes. So this is called as splitting. Right? Now, to split this node, there are certain rules. Those we need to follow. Okay? So, what are those rules? See here, take the n pairs including the one being inserted in sorted order and place first n by 2 in the original node and the rest in a new node. What does this mean? See here, this node we would like to split now because there is no room to accommodate new search key value, that is Adams. So the very first thing that we are going to do is, whichever are the search keys, those we are going to arrange in sorted order. So in sorted order, we will have Adams, then Brand, then Califieri, and then Crick. So this is the sorted order of the search key values. Right? Now, what we are going to do next is, what is n here? 1, 2, 3, 4. N is equal to 4. So, first n by 2 values. First n by 2. N by 2 means what? N is 4. 4 by 2 means 2. So, in this sorted order now, first two values, Adams and Brand, those will go into the first node. Right? And the remaining values will go into the second node. Are you getting me? Yes? Are you getting me? Right. So this is how, yes? Yes? Any doubt?
No, ma'am.
Fine. So, in splitting a leaf node, what we are going to do is, if the leaf node is full, then we are going to split the node. So, while splitting the leaf node, we are going to arrange all the search key values in order, and depending on this value of n, first n by 2 values will go into the first node and remaining values will go into the second node. Right? What next we are going to do? These are the leaves now. So for these leaves, we are having some internal node. Right? So this leaf node gets split into two nodes, but we are having some parent for this leaves. Right? Now, what we are going to do next is, in the parent of this nodes, right? The parent of the node, we are going to do is, in this split, this is the new node that we have added. So let us assume that this new node is P, right? And this K is the least search key value that is being stored in this new node. Then what we are going to do next is, this search key value K along with this pointer P will be inserted in the parent node. Right? So after splitting the leaf node, we are getting these two nodes. So this is the new node that we have created. And these are the values, those are stored in this new node. So what next we are going to do is, whatever is the least key value K and the pointer to this node, that is being stored in the parent, so that this node can also be reachable. Right? So this caliphery, in this situation, this caliphery will go into its parent along with the pointer to this node. Right? Now, it may happen that whenever we would like to insert this search key value in its parent, it may happen that the parent is also full and there is no space now to accommodate this search key value in the parent. It may also happen. Right? So if this is the case, then what we need to do is, we need to split the parent also. But the process of splitting a leaf node and splitting internal node is different. I'll repeat, the procedure for splitting a leaf node and splitting a parent node is different. So right now we have seen the process how to split a leaf node. After splitting a leaf node, the search key value along with the pointer of a new node need to be stored in its parent. If there is space in the parent node, then there will not be any problem. But if the parent is also full, then we need to split that parent also. Right? Now, this parent is obviously the internal node. So, let us see now how to split a non-leaf node. We have seen the process of splitting a leaf node. Now, let us look at the process how to split a non-leaf node. Right? So, whenever we are inserting a search key value pointer pair into already full internal node, say n, then what we are going to do is, we are going to copy this node n to a temporary location m with space for n plus 1 pointers. So if I am having earlier 4 pointers in the node n, then I'll be copying this node in new temporary space, say m, new node m, such that this new node m is having 5 pointers, n plus 1 pointers. Right? Why? Because I'm adding one value over here. Right? What next I'll do? I'll copy all those values in m, no doubt. Right? Now, what I will do next? I'm having now two nodes. Right? Parent has been split. Parent is split. Right? So, this is the old node, old parent node, say n, and I'm now, after splitting, I'm creating a new node n dash with same number of pointers. So earlier, if my node contains 4 pointers, then this n dash also contains 4 pointers. Right? And whatever was the data of this node n, I'm going to store this in a new temporary node. This m is temporary with n plus 1 pointers, so 5 pointers. So, right? I hope you must have understood. Right? Old node is having n pointers. This node is full, so I'm splitting this node. So obviously I'm creating a new node n dash with 4 pointers, suppose, right? But I'll be storing all this data of this node into a new node m with n plus 1 pointers, right? And I'll be arranging all this data once again in sorted order. Right? Now, what I will do next? I will copy P1 K1 up to pointer Pn plus 1 by 2 from this temporary node M back into this original node N. Right? What next I will do? After this Pn plus 1 by 2, I am having one search key value that I am going to ignore right now. And that search key value is k n plus 1 by 2. So right now I am going to ignore that search key value. Right? So what I will do next is, see here, from P1 up to pointer n plus 1 by 2, I am storing in this node n, and pointer P n plus 1 by 2 plus 1 till Pn plus 1 from this temporary node, I'll be storing in this n dash new node. Right? And what I will do is the intermediate search key value, that is kn plus 1 by 2. That search key value along with the pointer address of this n dash will go into its parent. So this is the procedure for splitting a non-leaf node. I would recommend that you should note down this algorithm. You will not find this algorithm anywhere. So I would recommend that you should note down this algorithm. And based on these processes, we are going to solve the problems now, so that you can understand and you can able to create the B+ trees. Right? So, see here, this is my original index. I'm simply giving you the example now. This is my original index, right? And I would like to add the search key Adams. So what will happen? I will check this node. So Adams is less than Mozart, right? So I'll be following this pointer. So this pointer will take me to this node, right? Now I will look for this Adams over here. I do not find Adams, right, in this particular node. So what I will do? I will check for a key which is greater than Adams. So I'll check here, I'll find here this Einstein is greater than Adam. So what I will do is I will follow this pointer P1 of this node, and this pointer P1 will take me to this. So I may find this Adam in this particular node, but what I find is Adam is not present in this leaf node. So I need to insert that new search key value in this node. But now this node is full. As this node is full, this node is being split. So if this node is being split, then as I stated earlier, we'll be having two nodes now instead of this one. Here we are having n equal to 4. So first two values. So the values are arranged in sorted order. So Adams, Brandt, Califeri and Crick. So first two values will go into the first node and next two values will go into the next node. Right? So after splitting the leaf node, what will happen is Adams and Brandt will go in one node, Califeri and Crick will go in other node. As I stated earlier, this lowest search key along with the pointer to this node should go up in its parent. Now, this parent is having one space empty, right? So, as this space is empty, the new search key value can be accommodated in this particular node, right? So, Calipari can be accommodated in this particular node. So, once again, we need to arrange the search key values in ordered manner. So, in this particular node now, whenever Calipari gets inserted here in this internal node, I will be having the search key values as Calipari, Einstein and Gold. Okay, so this Calipari will go into this first place. Now, the pointers are being updated such that this P1 of this node will point to this particular node having Adams and Brand. This P2 will point to the node where I am having the key values Calipari and Crick. This P3 will be as it will be pointing to the same node. Earlier also this pointer was pointing to this node and this pointer will point to the node where I am having this Gold. Right? So after inserting a new value Adams in this B plus tree, I'll be following the process and I'll be coming out with this output. Right? I hope you must have understood the process. And now we are going to practically build a tree from scratch. So that once again we are going to apply all the rules. Those we have seen so far. Right? So shall I proceed with the problem? Yes. See here, I am having one more example wherein Lamport is being inserted in the earlier B plus tree. So after following the similar procedure, we have created this B plus tree. Here we have inserted Lamport into this particular tree, in this particular tree. The new search key Lamport is being inserted into this tree. And after inserting a new key, I'll be having such kind of a B plus tree.